Sir,
Friends, I hope
sir, I have started the recording, sir. You can
record it.
continue, sir.
Facing some recording issue.
Sir,
Okay. It seems someone is recording. Someone else.
sir, I have started the recording, sir. You can start, sir.
Can you hear me?
Yes, sir, I have started the recording, sir. You can start the class, sir.
Okay. I think I'm only having some issue with the recording. Okay. I'll see through it.
After the class, I will share you the recording, sir.
Okay. Okay. No problem. Man. Okay. So I hope it is fine now. And till last class, we have dealt with the Newton-Raphson method. Okay, so we have dealt with the Newton-Raphson method, and today we'll be dealing with the fast decouple method. So before getting on to fast decouple method, you have to know some terms. Okay, you have to know some terms regarding this sparsity of the matrix. You have to know, and then decoupling you have to know. So these two things you have to know about. So after that, we'll be getting into your fast decouple load flow algorithm. So it is a simple concept only. So it is a more or less theoretical part. It is easy to understand. It is nothing but the extension of your Newton-Raphson method. Okay. So it will be easy to understand, and it will get over soon also. There will be slight modification with respect to Jacobian matrix. Okay, that's the only difference between your fast decouple as well as your Newton Raphson. So before getting into that, you have to know about what is decoupling. Okay, and then sparsity you have to know. So generally, I'll be dealing with the sparsity first. Generally, sparse, the term sparse refers to small term. Okay, or you can consider it to be as a small value. Okay, small term or small value. So what happens? You in the formulation of your load flow, your initial step is formation of your Y bus or your admittance bus. Okay, formation of your Y bus. So generally, this Y bus is a combination of or a matrix format of your all the admittance matrix format of all the admittance value. Okay, so this is the general concept, you know. But comparing to your Y bus, can anybody say you already know there is this Y bus value is nothing but your reciprocal of your Z bus. So, can anybody say which bus, Y bus or your Z bus, which bus will be having a very low value? Whether it is Y bus or it is your Z bus. Which bus
Sir, if
matrix?
Z bus value is low, then Y bus value will be high. Or
Yes.
if Z bus value is high, Y bus value will be low, sir.
Yes, generally your Z bus value will be high because it consists of your impedance values, and hence your Y bus value will be very less. And this uh, value, that is the small value of your Y bus, raises your sparsity. So sparsity is nothing but the lower value. When you're forming your Y bus itself, you might have went through. You'll be getting around some around 0.00 something like that, 0.1 like that. And most of the case, your Y bus will be of symmetrical. Symmetrical, that too, uh, it will be with the diagonal elements. That is, your diagonal elements alone will be present, and your off diagonal elements will be maximum. It will be 0. Okay, in the most cases, either it might be of upper triangular matrix structure or it might be of your lower triangle. Like that, it will be. In most cases, these off diagonal elements will be 0. So this rises to the sparsity. So you just have to know sparsity in the sense it is of a very smaller value. The matrix is of a very smaller value. Okay. Also, this sparsity rises. Why it rises means at the diagonal elements. So at the diagonal elements here you can see at this diagonal elements only the more number of buses will be connected. Okay. If you are considering a single bus, if you are considering a single bus and it is connected with the n number of buses means most of the cases the diagonal elements represents the interconnection between all the other buses, and hence this diagonal element value will be of higher in value. Okay. And this is what the major thing you can notice in your what you can say in your power system network. So what are the advantages this sparsity raises? Okay.
Sir, can you repeat that? Why the Y bus value will be small terms once again, sir?
Okay, I'll be coming from your sparsity matrix. So first you have to know about sparsity. So generally the sparse in the sense as the value, as the meaning says, it is small value. Okay. So in your transmission network, your Z bus, okay, your Z bus will be of higher. Why in the sense means this Z bus is acts. It will be a barrier for the excess amount of your current flow. Okay, in such case, that is if there is a sudden load. Okay, if there's a sudden industrial load. You know that industrial load draws excess amount of current. If there is a sudden rise in the industrial load, what happens is that the current flow will be also very high for a particular moment. For a momentary duration, it will be very high. The current flow will be very high. So the impedance value will be there to restrict your current flow, and hence your Z bus will be, that is your Z impedance value will be generally high in your power system network. Okay. But regarding with your load flow analysis, okay, regarding with your load flow analysis, our first initial step is the formation of your Y bus. You won't be considering your Z bus matrix for the load flow analysis. Okay, and hence for the formation of the Y bus, it is nothing but the reciprocal of the your Z bus. So you have to reciprocate your Z bus to get your Y bus matrix. So this, while you are reciprocating, most of the values what you'll be getting will be of a very very small value. In some cases, you can also round off it to nearly zero. Okay, so such kind of matrix formation is called as sparse matrix, and this property is known as sparsity. Okay, uh, I hope you might have understood. Okay, these kind of formation, this kind of matrix is called a sparse matrix, and this kind of feature, the exhibiting feature by this matrix is refers to the sparsity. Okay. Uh, Next is that I hope you might have got it. After this, we'll be moving towards advantage. What are the advantage on basically of this sparsity feature we'll be seeing? I hope you got it current, right? Why this Y bus is small? I have just now said to you. Okay, we'll be moving out. Advantages of sparsity matrix or sparsity feature. Okay. So the first advantage is their storage. Their storage requirement is small. So obviously, you know that if the values are more or less negligible or small in the sense, the storage requirement will also be very small. Okay, it is small even for a larger system, even for a larger system, even for a larger system. Okay, so the second point is that direct solutions can be obtained. Okay, uh, that is, the solution solving capability is fast. Capability is fast as direct solution are obtained. That is what they're trying to mean is the computational methodology is very minimized. The complexity in computation is minimized due to this sparsity. Okay, and after this, third one and final one is round of errors are minimized. Okay, so this with respect to your sparsity. Okay, so this they might be asking you in your 2 marks separately. In your 2 marks, they might be asking you. Okay, and going to the next part is about your decoupled method. Okay, so decoupled methodology. So the next part what you'll be seeing is fast decoupled method you'll be seeing. In that, before getting into that, you have to know about what do you mean by decoupled method. Okay. So as I said, in your power system for the load flow, you have to consider four components. You have to consider four components. So can anybody name what are the four components? Can anybody name what are the four components? we have seen. So there will be 4 components we'll be considering. What are those?
Generator, load.
Uh, can you come again?
So the generator, load, those things.
That's it. Generator load. Those and all will be representing it as what kind of bus?
PV,
Yeah,
PQ,
yeah. So those are the 4 components. So first one is your P, which is nothing but your real power, and the second one is your Q, which is nothing but your reactive power, and after that it will be V. So it is your voltage, and then del, that is your voltage angle. So these are the 4 components. And can anybody say whether these four components, these 4 components are interdependent with each other or not? Can anybody tell me whether these 4 components are interdependent on each other or not? Just think and say, tell me the answer. Whether they are dependent on each other or they are not dependent on each other. Simple question. This is a question. Hmm? Just ask yes or no question only. You just tell me whether they will be dependent on each other or not. Okay, you can just answer whether they will be dependent or not. Is Mohammed there? Mohammed Ashik. Mohammed Ashik, are you available? Okay, you tell me whether these components will be dependent on each other or not. You can just unmute and say. Try to be a little bit interactive because so I am over here as placement coordinator. Okay, so what is the feedback I am receiving from you as, for your seniors in terms of the company is that they are not interactive. Okay, in most cases they are not interactive. So they are just missing out their chance. Okay, so try to be interactive at least when I am asking the question. Okay, moment you can just unmute and just say. Okay, I think he went to idle state. I think I have to reduce the marks when you are not answering the questions I'm asking. Okay, is Kailash Kumar there? Kailash Kumar. Kailash Kumar. Okay, most of the students are leaving. Okay, I will be just proceeding with it. Okay, these 4 components will be interdependent on each other. Okay, these 4 components will be dependent on each other. So, and hence they'll be contributing to your buses. Okay, we know that there are 3 type of bus. So, first bus will be first slack bus will be of generally it will be slack bus will be of what you can say for just for reference. but the other two buses, PQ and PV, here you know that these two will be of dependent, these two will be of dependent. Yet as these four components are dependent on each other, the dependency link or the link between some components will be weak. Okay, for example, the coupling between your real power and your voltage. Okay, that is the coupling between your real power and your voltage. Okay, and the coupling between your reactive power and the angle, voltage angle. Okay, so this coupling or the dependency, these two dependency or the coupling will be uh, what you can say will be minimum, or it will be somewhat weak, and hence what you can do is that as it is weak, this weak coupling can be utilized for a solving of method. Okay, the new method, the decoupling method, revolves around the uh, weak linkage between your reactive power and voltage angle, as well as your real power and your voltage. Okay, based upon this only, the what you can say, the decoupling method is evolves. So what happened is that can just write it out. The weak coupling between, first one is your real power, which is nothing but, and voltage, bus voltage, and reactive power, Q, and voltage angle, okay, is utilized for the development of decoupled method. Okay, okay, I hope you got clear. And how we'll be getting is that, you know, the equation, power residue equation, what we have seen with respect to your NR. As per that, the power residue equation is del P del Q will be equal to your Jacobian matrix J1, J2, J3, J4, and over here it will be del del, and over here it will be del V. So this is the equation that we have got. Okay, so this is the equation that we have got regarding in your NR methodology. Okay, while dealing with your NR method, this is the equation that we have got. And now, as per the decoupling methodology, as and your sparsity feature. Okay, as per your decoupling method and your sparsity, what you can say, sparsity feature. From the sparsity, what I said, your diagonal elements will be of larger value, whereas when you are comparing to that of your off diagonal elements. So these two values you can just neglect it. J2 and J3 you can just consider it to be as a negligible value. and you can represent your del P and del Q as, okay, you can represent your del P and del Q as power residues as del P equal to this J1, okay, into del del, and over your reactive power, what you can take it as del Q equal to J1 is over, so J4 will be there, so J4 del V, okay, and this is the main difference that is contributing with your Newton Raphson and your decoupled method. So this is a decoupled method. So after this, we will be moving towards your fast decoupled method. Okay.
What happens to the J2 and J3, sir?
So that's it. As per the sparsity feature, you have to see. So as here, sparsity feature I have said, right. So in the sparsity feature, what they'll be doing is generally they'll be neglecting these two values if they are of very small value. So that's what sparsity is. And dealing with the problem, this you might have also studied in your matrix problem also. There's a separate property called sparsity of a matrix. So in that, generally you will be considering your off diagonal elements to be 0, and the same thing happens over here. For the decoupling methodology, since the link between your P, okay, P and your bus voltage are weak, okay, this P and your bus voltage means if you are multiplying means it will be multiplied with the term of J2, okay. If you are just taking a matrix multiplication means, so what will be getting, you'll be getting around the value of del P will be equal to J1, okay, J1 into del Q, del, okay, del plus J2 into del B, okay. So this is what the matrix multiplication over here. And over here, what happens, the occurs two things. As per the sparsity, this J2 will be 0, as well as there occurs a weak linkage between your del P and del V, okay. And hence what happens, this gets negligible, okay. So this gets negligible and you'll be getting this term. The same is applicable for your del Q also. Del Q, it will be J 3 of del, okay, plus J4 of del V. And over here what happens, the term which will be negligible is this J3, okay, and hence you'll be getting this element, okay. So I hope you just understood about the decoupling methodology and your what you can say, sparsity, okay. So these are the two things I had to see. And in the next class, we'll be dealing with your what you can say, we'll be dealing with your fast decouple. We'll start with the fast decouple, and if possible it will be completed within the next class. It is a small concept only there will be some changes with respect to your NR methodology. Other things will be the same, okay. Um, so today's class, I think we'll be stopping with this decouple method. And okay, so any doubts you can just ask. Any doubts is there, you can just ask to me.
No, sir.
Okay.